Media.
When we look at a sunset, we see waves of light energy that have traveled an immense distance to reach our eyes. When we look at an ocean, we see waves of water energy that may have journeyed thousands of kilometers to reach our shores. Most waves derive their energy from the wind. As the wind blows over the ocean, some of its energy is transferred to the surface, forming waves that move through the water. And it is in large part the power of these waves that makes the coastal environment such a dynamic place.
Coastal areas are among the most beautiful and desirable places anywhere on Earth. The coast and coastal landforms like this beach are the result of a dynamic interaction between two competing geologic agents, the rocky land masses and the energy of the ocean. People tend to think of these as separate and independent from one another. But by ignoring the intimate connection between land and sea, they fail to realize that this delicately balanced system is subject to continual change. Building walls and boardwalks and homes on a shifting coastline is a gamble with nature that sometimes pays off with disastrous consequences. Clearly then, the coast is a part of our world that needs to be observed and understood. Consider the waves, for example. Their rhythmic motion and sound has made watching them a popular pastime. And yet few people have a real understanding of exactly what a wave is and how it works. And understanding ocean waves is vital to predicting their impact on not only the beach environment, but on coastal development.
When a wave approaches the beach, it's not the water itself that's advancing, but a surge of energy which is moving through the water. It's like the ripple that runs across a field of grain when the wind blows. The individual stalks don't run across the field. They simply bend as the wind strikes them. Or take the wave at a football game, which creates the illusion that the spectators are rippling around the stadium, when all they're actually doing is standing up and sitting down. The same principle applies to water waves. Consider what happens to a floating object as a wave of energy passes through the water. That object tends to stay more or less in the same place, tracing a circular motion as it bobs up and down. The individual particles composing the wave behave in a similar way. As the crest of the wave arrives, it lifts the particle up and forward, and then when the trough of the wave follows, the particle falls down and backward. Like the stalk of grain or the football fan, the particle returns to its original position after the disturbance has passed. At the water surface, the circular orbit of the water particle has a diameter that is roughly equal to the height of the wave. As one looks below the surface, however, the orbit gets smaller and smaller until there is virtually no motion of water at all. The downward limit of wave motion in the water is called the wave base, and it's directly related to how far apart the waves are at the surface. The depth of the wave base is equal to about half the wave length, which is the distance between the crests of two waves. As the wave approaches the shore, and the water becomes shallower, the sea floor intersects the wave base, confining the wave energy. The wave now starts to slow down as the sea floor begins to interfere with the orbital motions. This forces the wave up and shortens its length, because waves behind it, still in deeper water, are advancing faster and begin to overtake it. As this happens to a succession of waves, they bunch up like cars in a traffic jam. As the bottom of each wave is slowed by the frictional drag of the seabed, the top continues to surge forward, making the wave steeper and steeper. Eventually, this steep front can no longer support the wave, and it breaks into surf.
Perhaps the ultimate ocean wave is the seismic sea wave, otherwise known as a tsunami. Tsunamis can strike coasts without warning. With wave heights sometimes exceeding 30 meters, these waves have a potential for death and destruction that makes them the subject of legend throughout the world. Unlike ordinary wind-generated waves, tsunamis are caused by a much more powerful force, earthquakes. Undersea and coastal earthquakes can cause the ocean floor to shift suddenly. This movement of the ocean floor displaces a vast volume of the overlying water, creating these unusual waves. Tsunamis are tremendously fast-moving, some traveling in excess of 800 kilometers per hour. The wavelength of a tsunami may be 150 kilometers, and so the movement of the orbiting water particles within the wave will stir up deep-sea sediments even in the mid-ocean. Remarkably, however, such a tsunami may measure only a meter or so high in the open ocean. But as tsunamis approach the coast, they bunch up and rise monster-like from the sea. In a few minutes, tsunamis can completely devastate a coastal community.
One coastal community that experienced the crushing power of a tsunami firsthand was Hilo, Hawaii. On April 1st, 1946, following an earthquake off the coast of Alaska, one of the most destructive tsunamis of modern times sped across the Pacific and obliterated the entire shore zone at Hilo. The death toll that day was 159. Fortunately, tsunamis are not everyday events, but even ordinary waves have some impact on the shoreline. One very important process at work here is refraction, the bending of wave fronts as they approach the shore. When a wave approaches the shore at an angle, the near-shore stretch of wavefront reaches the shallow water first and is therefore slowed down first. This local decrease in velocity causes the wavefront to bend or refract because the deeper water portion of the wave continues to move at its original speed. As a consequence of this refraction, the waves near shore tend to approach the coast nearly head-on, while those in deeper water continue along their original course. Wave refraction has its greatest effect on irregular shorelines with deep bays and projecting headlands. Waves are refracted towards headlands, smashing into them from both sides. At the same time, they are spread out in bays. In other words, wave energy is concentrated on headlands and dispersed along the shoreline of bays. The net effect of refraction on irregular coastlines is to straighten them out. As the waves crash against the headlands, they erode sediment, then deposit it as sand in the bays. So the waves perform a double action, simultaneously wearing away the headlands and filling up the bays. The erosion of coastal headlands is by no means the only source of sand. Most beach sand comes from sediment that is brought down to the ocean by rivers and streams. Once the sand reaches the ocean, the waves distribute it along the coastline. This occurs as a result of wave movement up onto the sloping part of the beach, then back down again. Each cycle of wave movement carries particles up and down the beach slope. Because waves usually break at a slight angle to the shore, the grains of sand in this cycle are gradually worked along the shoreline in a zigzag path.
Sand gets moved along the beach face by the waves approaching the coastline at an angle, and when the waves break, they have the momentum from their falling forward at that angle. So the waves rush up the beach face in the swash zone at an angle, but then gravity's going to pull that water straight back down the beach face. So what you and I see is kind of an arc shape of water swashing up and then going straight back down. And the result is that as this occurs thousands of times a day, the sand moves in kind of a zigzag motion up and down the beach face.
The yellow dye shows this movement. This flow of water along the shoreline is known as the longshore current. Sand spits and baymouth bars are common products of longshore currents.
What happens is that the sand is being carried along the coastline, the beach sand, and when the coastline reaches, say, a right angle turn, an abrupt bend, the beach will tend to be carried still by that longshore current straight along the coastline, so that the beach will start building out and creating a extension of the beach that will not necessarily follow the bend in the coastline.
In this case, a sand spit has formed off the end of this breakwater. This wave tank shows how the sand spit built up. The waves strike the breakwater at an angle and bend around it into the harbor. When sand is added, the waves carry it into the harbor where it builds up into a spit behind the breakwater. To prevent the harbor from being sealed off and the beach beyond from being deprived of sand, engineers installed a dredge to pump the sand back into the longshore current by picking it up in the harbor and dumping it further down the coast. Not only do beaches change continuously as sand is moved through them by the longshore current, but seasonal changes occur as well.
The beaches change from season to season. By summertime, the waves are fairly low and gentle, and that has a tendency to drag sand towards the beach and build up the beach and make it broader, wider. And as it piles up, the sand has a fairly gentle slope. In the wintertime, though, the larger waves, more energetic waves, pick up that sand, tend to move it offshore, and store it in large sand waves, almost like underwater sand dunes. And so the beach becomes very narrow. What sand is there is very, very steep and slope. And most of the beach is really located offshore, finding a more stable position under that bigger storm waves.
The beach is just one part of a much larger system that regulates the formation, supply, and deposition of sediment along the shore. This system includes the mountains, where weathering processes turn rock into sediment, the rivers, which transport that sediment to the coast, and coastal processes, like the longshore current, that redistribute the sediment along the shore. As we've seen with breakwaters, however, people can easily disrupt the natural balance of this system and alter its ability to operate normally. Dams are another example of our attempt to control natural processes. These structures serve a variety of valuable functions: the generation of hydroelectric power, the establishment of lakes for recreational purposes, and in this case, flood control and the storage of water for drinking and irrigation. Despite their value, dams are not without significant drawbacks. Sediment that is normally carried downriver to the beaches is trapped in the reservoir instead. Beaches that don't receive a steady supply of river sediment will soon disappear. It is tempting to cast people as the villains in this apparent conflict with nature. But the issue is not that simple. What would happen if we didn't dam rivers? Would we be willing to risk the exposure to catastrophic floods and to give up the electrical power and the fresh water that dams provide? If not, is the damage they cause to coastal property and to the beach environment too high a price to pay? These are difficult choices, and there are no perfect solutions.
Problems often arise as a result of special circumstances. During severe storms, for example, crashing waves can batter coastlines. Such storms occur only once every few decades. But in the quiet periods in between, people tend to ignore the historical record of erosion and build along the edges of the shore. To protect the ocean view homes and hotels that are perched atop sea cliffs and along beaches, sea walls have been erected that reflect the energy of the waves away from the coast and slow down erosion. However, what may have sounded fairly straightforward in theory has become quite controversial in practice. Those in favor of seawalls argue that the cliffs must be protected to safeguard the real estate above them. Those who are opposed maintain that in the long run, seawalls do more harm than good because they represent a threat to the beach itself.
Coastal erosion is a natural process. As we begin to put houses on the edges of coastlines, we're concerned about losing some of those homes, and so you want to slow the erosion. Well, you're trying to slow something that's quite natural. When you do that, you upset the balance of things. Seawalls, to limit erosion, are also cutting sand supply. And so putting in a seawall will, for a short period of time, lessen the amount of erosion. But what the result is that sediment is no longer there to be taken to the beaches. The beaches receive part of their sand supply from cliff sides. And as you slow down the erosion of cliff sides, then the beaches are losing a source, an important source of their sediments.
Another problem is that the flat surface of a seawall reflects much of the wave energy directly back toward the beach. Unfortunately, this can erode the sand at the foot of the wall, eventually undermining it. At the Scripps Institution of Oceanography, scientists deal with this controversial issue on a continuing basis.
Wavelengths now?
Scott Jenkins of Scripps Center for Coastal Studies is one of those involved in the design of seawalls, breakwaters, and other coastal structures.
That's correct. 20 degrees of obliquity. All right, so...
The goal is to design structures that do the job with a minimal negative impact on the environment. Jenkins and his colleagues use a wave tank and scale models to test their designs, in this case a breakwater. Sensors placed around the tank measure the heights of the waves both inside and outside the breakwater, giving Jenkins an indication of its effectiveness at reducing wave energy. Data from the experiment is fed into a computer, allowing the scientists to refine and retest the design before an actual prototype is built. When designing the seawall, Jenkins and his colleagues turned to nature for inspiration. The irregularly shaped surfaces of sea cliffs and coral reefs reflect a minimal amount of wave energy. So the Scripps scientists decided to incorporate nature's energy-absorbing design into their seawall. So far, this wall has been a success. The property has been protected from further erosion without destroying the beach at the base of the wall. But while Jenkins is committed to building the most effective sea walls he can, he recognizes that they are only a short-term solution. And he is sensitive to the arguments of those who oppose attempts to redirect or in any way modify natural processes along the coast.
There's a wide variety of environmental groups, and there's a wide range of government officials and university professors who oppose construction and structural intervention on the shoreline. And the reason is philosophical, that we want to preserve the shoreline in its natural state. Now, those who are going to lose property if erosion continues also have a concern, and those are the people who, of course, are going to favor these structures. And my personal belief is we should adopt the policy of maintaining the coastline in its natural state. And a large part of that policy would involve bypassing of sediments around dams and preventing further encroachment of coastal structures in the nearshore area. And then I would say, having made those fixes, let the system adjust to its own equilibrium. There's far too much energy out there for man to compete against.
Jenkins contends that doing a better job of transporting sediment around dams would be an important long-term solution to the problem of beach erosion.
Basically, it's an earth-moving problem, and we already have a very well-developed technology in earth moving. Now, in Southern California, and in many other areas as well, there are seasonal fluctuations in the lake level, and typically the lake levels are low in the summer, but whatever season they're low, earth-moving equipment can come in and excavate these sands from the dry foreshore area. The foreshore deltas in these reservoirs contain most of the beach-sized sand, and these will be high and dry when the lake levels are low. So they can be collected with standard earth-moving equipment and either trucked directly to the beach or reintroduced to the stream beds downstream of the dam.
If there is technology and engineering available for transporting sand around dams, why isn't this being done? One reason may be that many scientists originally rejected the idea that dams actually contribute to erosion. But that is no longer the case. The problem currently seems to be that the value of sand as a coastal resource may still not be fully recognized.
A lot of this sand is already excavated by sand and gravel companies for construction material. It should be treated as a public resource and a fair market value paid for it. For instance, people on the beach would be willing to pay many dollars per cubic yard for nourishment sands, sands that sand and gravel companies haul away at just a fraction of $1 a cubic yard. So this needs, I think, to be regulated just like water and treating sand as a public resource.
Regardless of how the battle over seawalls and sediment supply eventually turns out, coastal dwellers will always have to deal with incursions from the oceans. In addition to problems caused by crashing waves, there are a number of other factors that affect the level of the water. The most familiar is the action of the tides. Tides are primarily the work of the moon and, to a lesser degree, the sun. As the moon orbits the Earth, it exerts a powerful gravitational pull. This causes the ocean on the side of the Earth facing the moon to bulge out slightly. Another tidal bulge occurs on the other side of the planet as water lags behind due to weaker gravitational attraction from the moon. These bulges create a high tide. High tides can create tremendous havoc, especially if they're combined with violent storms. This is what happened in 1970 in Bangladesh, when a cyclone combined with a spring tide flooded the delta of the Ganges River, drowning 250,000 people. But such tidal disasters are rare. Most of the time, the twice-daily ebb and flow of the tides only brings about small, brief changes in the water level. But there is also a long-term change going on all the while. Since the peak of the last ice age tens of thousands of years ago, melting glaciers have spilled immense quantities of water into the oceans, causing a rise in sea level of over 100 meters. Such a global change in the volume of water in the ocean is known as a eustatic change. Although today's sea level is much more stable than it was at the time the Ice Age ended, a small eustatic change is still going on. The glaciers of Greenland and Antarctica are continuing to melt faster than they grow. This causes a small but steady rise in sea level worldwide. However, between now and the year 2100, there may be a significant increase in sea level due to the so-called greenhouse effect. Carbon dioxide and water vapor in the atmosphere act like the glass of a greenhouse. They let in the sunlight, but trap some of the re-radiated infrared heat energy. Without this greenhouse effect, the Earth would become too cold to support human life. But since the Industrial Revolution began to mechanize our world in the late 18th century, we've been adding tremendous quantities of carbon dioxide to the atmosphere by burning fossil fuels. The first of these was coal, the fossil remains of vegetation. Burning coal produced the steam which powered steamships, factories, and locomotives. It also released vast amounts of carbon dioxide, which until then had been stored underground for millions of years. Since the early days of the Industrial Revolution, the world's reliance on fossil fuels has increased dramatically. Today, these fuels include not only coal, but gasoline and oil. If we continue to burn these at our present rate, the amount of carbon dioxide in the atmosphere will increase significantly. This could magnify the greenhouse effect to such an extent that air temperatures could rise by several degrees and accelerate polar ice melting, which would result in a rise in sea level of a few meters. This may not seem like much, but it would be enough to flood many of the world's coastal communities.
Although the coastline appears to be a stable and permanent fixture of the landscape, it's in fact a place of inevitable change. When people choose to live here, they become subject to that change and run the risk of losing everything, either suddenly or steadily over time. Permanent protection for coastal development simply doesn't exist, and many protection schemes actually degrade the quality of the beach that attracted people here in the first place. As a result, it's becoming increasingly important to develop a wise coastal management policy that incorporates the most current scientific knowledge with the needs of the environment and of our communities. It's clear that there's a significant role for geologists, and indeed for all of us to play, in learning to protect the coastline for ourselves and for future generations.